Okay, so in the previous lectures, I was talking about how some product is related to entropy, to beta entropy, and messages, dual variables, and all those things. But now we are talking about a different problem, the max sum problem. So what is the map inference? Maximum posterior inference for the graphical models. And we use a very pragmatic approach, which is called augmented Lagrangian. Of course, all of these things are related. I'm looking at it from different perspectives. So I want to explain one of the articles of Andrew Martins. And Noah Smith and Eric Shing. Eric Shing is a great teacher. He teaches very complex things like beta approximation very easily, so that everybody can understand and appreciate it. And Martins, he's interested. For example, he has many articles on dependency trees. He uses in some of his articles he uses linear programming relaxations and Lagrangians, like this article, and in some of his articles he uses just the message passing, loopy belief propagation, but he reformulates dependency parsing on factor graphs. And of course these are really important articles by your Weiss. And I will also explain this article by Foruzan in the next lecture, and his supervisor Alexander Ehler. So these are working on map inference, but using augmented Lagrangian. And ADMM, I've explained ADMM, alternative direction of method of multiplier, in my playlist for optimization methods. So he's a great scholar. So the idea is to combine the dual decomposition. I have a playlist for this dual decomposition in natural language processing and parsing. And also augmented Lagrangian, which is a classical thing in optimization. We combine them and we call this method dual decomposition ADMM, because you're using alternative direction method of multiplier. So if you watch my playlist for dual decomposition, I've explained some of these articles. And the key features of DD-ADMM is that it is suitable for heavy parallelization, because ADMM provides some slave. You can think about it like some slaves, many subproblems, and there is a master that relates these subproblems together. So it's very good for heavy parallelization. And it is probably convergent even when each slave subproblem is only solved approximately. Consensus among slaves is fast by virtue of the quadratic penalty. ADMM uses augmented quadratic term, which is a kind of problem for some people. That's why some people approximate it. But we need that because it provides a robust things. What if your Lagrangian goes to infinity? So it's a kind of regularization term that we add, and that quadratic penalty. So if you're using this ADMM, it has consensus among slaves. And also it, in addition to providing an optimally certificate for the exact map, it also provides guarantee that the LP relaxed solution has been found. So this is the map assignment on factor graph. You have seen this form several times. And we want to know now the max set, the max sum. I mean, the maximum probability of this. I explained in previous lectures that we go to what is parametrization. We go from mu to from theta to mu, and then we extend it. We approximate the mu by the outer bound, which is L. So we should obtain this tau probability instead of these sufficient statistics mu vector. We have now tau vector, but then tau should satisfy the constraints. So you should also know what is decomposition. It's very important tool in optimization. For example, here Z is here and is shared between these two objectives. So if you write the Lagrangian, you can say that when Z is equal to Z2, Z1 is equal to Z2, then it becomes then it becomes that this shared variable. So it satisfies that. And the dual function, you can think about as this slave 1. This is slave 2. Of course, this is just two sets, but we can decompose very complex things. So it can be summation of many objectives. So it's a general idea in optimization. And this is the dual decomposition. So using that Lagrangian multiplies lambda, we can say that your master, which is this dual problem, it controls the slaves. It says that how these slave problems are related to each other. And you either use the subgradient approach or the ADMM approach. This is the algorithm for subgradient approach. You update those dual variables, but the ADMM is faster. Although you add these quadratic terms, but this is for robustness. It makes sure that because sometimes your L could go very high, but this creates a better approximation. It is now more differentiable, bounded, and has good properties. If you add this, we call it augmentation of the Lagrangian. And then, so the objective is now this, and you solve this using the techniques of ADMM. We update these variables, and we can solve the problem. So we update those dual variables. And it's very easy for binary pairwise factors. For example, that Ising model, everything is simple. And also hard constraints. For example, Andrew Martins created a hard constraint that, if you remember in my playlist for dependency parsing, he has a hard constraint because it was in factor graphs. So it's a tree that looks on all nodes to make sure it is a tree. This is a kind of hard factor. So this is a dual objective and the best primal feasible solution at each iteration. I've explained turbo parsers in my playlist for dependency parsing. And this is the hard constraint that I told you. Because now here we can model the high order features such as siblings, grandparents. So it's very nice. So each variable in itself could correspond to edge. And for example, this constraint says that we not only look at this arc, but also we look at another arc which is implicit in this node. So combining them, we are It's like we are working with an high dimensional features in our dependency parsing.